In this video, I'm going to show this paper called Efficient Automatic Scheduling of Imaging and Vision Pipelines for the GPU. As the paper suggests, this work is about an autoscheduler improving upon an existing one from Andrew Adams that he did in 2019. And the improvement consists on targeting GPUs more efficiently. It improves on the cost model to consider GPUs. It improves upon the search strategy to search the state space more efficiently and more effectively in terms of compile time and getting better schedules. And it is focused on image and computer vision pipelines. First, I'm going to talk about the problem that this paper is trying to solve. Then the paper talks about the autoscheduler, the search strategy, the improvements to the cost model, and finally some results are given. As mentioned before, this work extends the Halide 2019 autoscaler from Andrew Adams, which is under reference of the paper. Also for Halide, there's very good tutorials on the web. And the Jonathan Ragan Kelly's thesis on Halide should be very good to understand Halide. And this is basically extended to target GPUs, something that this autoscheduler was not able to do well before. And also the target is complex imaging and vision pipelines. That's one of the strong points of Halide. There's other similar DSLs that could target other applications, but Halide should be the best or one of the best for targeting this type of applications. The speedups, one of the main goals is improve the compilation speedups by having a better state space search strategy, and are the numbers that they're getting for that, but also getting better schedules by searching more effectively the state space. And they achieve this 1.7x than existing solutions, and which are according to the results that we see at the end, competitive with what the human experts provided. Image processing and computer vision programs require particular attention for long-range fusion that introduce a trade-off between redundant computation and locality, as this triangle shows. If you go to one corner of this triangle, you're gonna get worse at the other two. For example, if you fuse too much, you get a lot of locality, but you have a lot of redundant computation and perhaps lose parallelism. If you parallelize too much, you can lose locality and computation, and if you don't fuse at all, you don't have redundant computations, but you lose locality and could lose parallelism. Okay, manually exploring all these options is time consuming. It's not practical for a human being to do, and it's difficult to predict ahead. The Halide language provides natural as a first-class construct, first-class construct way of separating the schedule and algorithm that facilitates the exploration of this state space. One thing that this paper talks about is the cost model, because we want to evaluate each of these many options without having to benchmark empirically the performance on the target machine. So the cost model uses a deep learning network trained with the expected performance in the particular hardware, for that particular option to speed up the exploration phase. The goal of this paper again is to efficiently explore a rich space of GPU schedules and achieve high performance on a broad range of computer vision and image processing applications in a scalable way. The three strategies that are introduced in this paper to explore the state space are freeze the cheapest stages, and this is to spend more time in the bottleneck stages. Hierarchical sampling, which is basically creating a structural hash for schedules to group them and evaluate just a representative to reduce the number of schedules evaluated. Also memoization to avoid evaluating similar substructures in schedules twice. And the algorithms combine program analysis and machine learning. The program extracts features related that affect the performance of GPU, and these features are fed into a light neural network that predicts the performance of that particular schedule. And the neural network not only takes features of the schedule, but also the algorithm, because both are important in predicting the performance, the algorithm and the schedule. And the deep learning model is trained on a large set of random pipelines, but also using real-world application programs in which I understand that it's taking one out of the sets to test the neural network to make sure that it's accurate and not overfitting. In the next few slides, I'm going to talk about the scalability problem. And one of the main problems that Halide and this paper address is the stencil computations. For example, an stencil can be changed. For example, let's say the blur example, which is one of the most common examples in Halide. You have a horizontal blur and a vertical blur. One is a producer, the other one is a consumer. So in here, a stencil basically is an operation in which the output of for a particular pixel, let's say the output in here, depends on the neighbors of the previous image. So the output of this one is going to be a computation of all these neighbors. So you can chain them like this. For example, you have this is a consumer of this producer, and this is a consumer of this producer. So you have a producer-consumer relationship. And you have to take decisions like, do I fuse these two, do I inline these two, or compute them separately, and do I tile them? He's going to talk more about that. And this type of operation is common in image processing algorithms, but also in physics simulations. For example, Navier-Stokes, that in general, anything that has tensors and gradients are gonna see this pattern, because basically the gradient is a differentiation between neighborhoods elements. So also, of course, you see in deep learning things like convolutional neural networks. These autoschedulers want to balance the trade-off between memory, locality, redundant computation, and parallelism. You want to maximize a performance goal of, let's say, energy efficiency, runtime performance, or memory, whatever the user decides. And for that particular goal, you're gonna find the right balance that gets you better to that point. And one of the options, as mentioned before, is, let's say you have two computations in a chain like this, and keep them separate. If you have them separate, they're going to be allocated in different blocks of the GPU, and you have block level parallelism, but you do not have thread level parallelism. Another option is tiling the blocks, for example, like this, that you basically say, okay, I'm going to break down the for loop into different extents. Let's say the outer iteration is going to be from 0 to 4, and that could be allocated in the blocks. Then you have another inner that is, you break it down further and say it goes from 0 to 5, and those are allocated in the GPU threads. And then the other for loops that you might have inside of here might be serial for loops that are run in each thread, and maybe you can unroll them to vectorize them into the particular CPU of within the GPU in the course. So tiling has a lot of decisions, and the optimal decisions depend on your hardware target architecture, in this case the GPU, depending on the GPU configuration and the particular algorithm that you're trying to solve and the dimension sizes. Then you're gonna find, according to that, the optimal tiling decision if you need to tile at all. The selection of tiles introduces a trade-off. If you have small tiles, it produces many blocks but few threads, and you don't keep the threads busy enough. And if you have large tiles, you have the opposite trade-off. You have less blocks but more threads across the streaming multiprocessors. And the sizes that they use is looks like powers of 2, like 16, 32, 64. Are typical choices for the innermost thread dimensions, and powers of 2 are common for the remaining dimensions. My bad. I don't know why they limited like this. These choices are more effective for the hardware. It might be. It doesn't specify why. At least I don't remember. But still, there's a lot of possibilities to consider. And basically, if T is the number of tile sizes and D is the number of dimensions, then this is gonna be the time expected to complete. And typically, like in deep learning, you have 3 to 4 dimensional tensor operations that are common. Even in image processing, you have videos, color videos that have 4 dimensions. Yeah, so because of this, it's important to have autoscaling. When the author mentions the tile size, I understand that he refers to the inner looping here. So if you have a large a large step or a large size in here, then this is gonna be smaller. The blocks are allocated in the outer loop and the threads in the next loop. So if this is large, of course this is gonna be small. And if this is small, then this is gonna be larger, which is what mentions here. Okay, so if we go further to tile this one, we get this, like this. So this is the block, the outermost, the next one is the threads, and then you have the serial unroll at the bottom. You can unroll it to have CD and things like that. Okay, yeah, the computations at the thread level are gonna be the auto mentioned at the shared memory, but this diagram is not from the paper. At the thread level can use registers, of course. In the cores, you can use local memory, but you also can use shared memory. So there's various options exposed at this level. And if this level, the innermost, the new tile is unrolled, then you can use things like instruction level parallelism, like SIMD and things like that. Okay, there are trade-offs again in this place. This reduces parallelism at both the block and thread levels. If this is very big, then these two are gonna get smaller, and they also may increase the strides among threads, which reduces the bandwidth. And of course, there's more options to consider in the tiling now. And basically we are starting to see that the tiling options grow very quickly, and tiling is just one of the optimizations. There are other schedule options as well. And it puts the example of a 3-dimensional stencil in a chain with input of regular image size can generate almost 3 million possible options, even for a chain of length 14. And now imagine that you have a convolutional neural network with 100 stages in more than 4 dimensions, and dimensions is very common. Yeah, of course, the CNNs are like this or worse. Another option is the fusion of computations. For example, in this you have the computation here. This consumer is consuming what this produces, and this consumes what this produces. So you have 2 stages, and they can be fused into one. And by doing that, you increase memory locality, so you move in this direction, and you rely more on local memory rather than global memory, which makes the program faster. And in GPU, this is particularly important because the data transfers across different blocks might be more expensive. But also you increase redundant computations, and this also increases the number of possibilities to consider, and along with the tiling conditions, or along the tiling options. And basically this summarizes the scalability problem, that why an autoscaler is needed. Okay, we have seen that for real world applications, the number of options for schedulers can be in the millions, and fully computing each of these million options in a particular hardware is impossible. It's not practical because some of these options can take tens of seconds up to minutes to evaluate the performance. And basically what both the Adams 2019 and this autoscaler are doing is using a cost model that extract features out of the algorithm and schedulers and feed it into a deep neural network to basically predict the performance for that particular choice. And evaluating that in a neural network can take microseconds, and from microseconds from minutes or seconds to microseconds. It could be speed ups in the millions. So yeah, so that basically makes the state space exploration feasible. The author talks about that neural networks often partition larger programs into smaller components that can be scheduled independently. And yeah, this works well. He mentioned that this works well for individual layers that have high arithmetic intensity and dense connectivity. So yeah, so basically it's not, for these cases, fusion might not be good, but I understand that it is convenient to somehow fuse layers. Like for example, you have three straight layers of convolution, ReLU, and pooling. You can fuse them. The point the author is trying to make is that these assumptions that optimizing the stages independently can work for deep learning architectures, but that's not the case for image processing pipelines and computer vision pipelines, because they have numerous relatively low arithmetic intensity operations that are interconnected sparsely, and therefore they require that the scales be considered together, and that introduces the trade-offs of recomputation, storage, locality, and parallelism. But I wonder if this applies also for convolutional neural networks for image processing and computer vision applications, because I understand that many of the operations that you see in image processing can be modeled in convolutional neural networks. I see the convolutional neural network as a generic image processing pipeline. So I wonder some of these things might apply also to CNNs. And they tried basically this empirically, and they found that the TVM did not perform well because it doesn't have fusion at all. TVM is basically another domain-specific language that it is targeted for deep learning, not for, unlike Halide, which is targeted for image processing and computer vision. Now we're going to talk about the autoscaler in this paper. As mentioned before, it extends the Adams 2019 autoscheduler, and the three main improvements are the hierarchical sampling, decision freezing, and memoization to allow the explore the largest space more effectively, improving compile time speed up, and also it inherits from the Adams autoscheduler the three major components of enumerating plausible Halide schedulers for GPU. Basically, it brings out the features of the schedulers and feeds them along with the algorithm to the cost model, and the cost model predicts the runtime. I wonder if also can predict memory or energy efficiency, but I guess that's trivial. It uses a variant of the beam search that Adams is using to explore the state space, and understand that the variation is the usage of these strategies like hierarchical sampling. And they also have the option of benchmarking the options in the GPU target, and basically use that to update the neural network cost model. I understand that this is the auto tuning option. Later he's gonna mention that he has three options. One is one shot, the other one is the top 5, and the final one, the most expensive one, is the auto tuning, that I understand can actually do benchmarking and update the neural network for cost model. This picture illustrates the hierarchical sampling strategy. So the choices are enumerated from the previous stage. So I understand that for each stage they consider one loop at a time and then go deeper, something like that. And once you have the choices, you group them. You have a structural hash that represents the schedule, and with that you find similar schedules and group them in buckets. And then you select the log 2 of the number of options. For example, this one has 4, this one has 2, and this one has 2, and the log 2 of 4 is 2, so you select only 2. The log 2 of 2 is 1, so you select 1, and those are the representatives that you're going to consider. And then evaluate the cost and use beam search to get the top K and keep going for the next phase. The different loop levels are considered one at a time. First, let's say they consider the block, and they're gonna make hashes for the schedule, and the hash depends on the schedule being considered. So, for example, in this case, you're considering only the outermost, which is the block level for loop. Then these two schedules are the same, and they have the same hash. But once you go deeper into a thread level, they're gonna be different. So you're gonna have a different hash for this. Yes, as mentioned before, they first go into the consider the outermost loop first, and consider the promising coarse grain candidates, and then go deeper into a more fine grain level. But I wonder if this precludes the possibility of finding better schedules. Let's say if you go in the other direction, let's say you try to optimize from the serial loops or the innermost rather than the outermost. And also, I don't remember them mentioning loop interchange, things like that, although I think they have some heuristics for that. Okay, we talk about a hierarchical sampling. Now let's go to the next strategy, which of exploring the state space, which is freezing. And freezing, as mentioned before, it focuses on the bottlenecks. It freezes the lower cost stages of the program, focus on the attention on the higher cost stages, that is the bottlenecks. And this is guided by the cost model. For example, a pipeline can have, let's say, the blur, you have a horizontal blur, vertical blur, you have two stages, and or let's say a convolutional neural network, let's say you have 3 layers, convolution, max pooling, and ReLU, and you find out that the convolution is the bottleneck, then you're gonna freeze the ReLU and max pooling and focus on the convolution. And the decision of what to freeze is driven by the cost model. This is important because at the end results, they show that sometimes doing freezing is not the best, and sometimes not doing hierarchical sampling is not the best. So yeah, it's good to know that they are using the cost model, the deep learning model, to know when to do it and when not. That's my understanding. That I understand that the model should be able to say, okay, I'm not going to freeze because for this particular algorithm and schedule, it's going to hurt rather than help. So I understand that the model should be able to include that if it doesn't. And this improves scalability. The final state space search strategy is memoization. And the author mentions that one of the most expensive operations is featureization. That's basically extracting the features from the schedule to feed it to the neural network of the cost model. And while the schedule candidates is rare that they are identical, maybe some substructures the substructures are more likely to be equal. So they applied this into the substructures, and they mentioned that the memoization has more impact on programs that favor schedules with separate kernels rather than fusing them. Okay, so in this diagram, he makes the point that, for example, let's say that you have this schedule, which is the same as this one right here. So for the first one, you get the features, you compute them, and memorize them. And then when the second one comes, it's the same, so you reuse the features of this one. I guess they pull them using a structural hash. They mentioned in hierarchical sampling that you have a structural hash to basically group them and select the samples. So I don't know if that same hash is used for memorization. I don't remember them mentioning it. And then if let's say that these two schedules are fused together, and now you have it like this, then this output, now you have to recompute them and memorize them again. Now we're going to talk about the search algorithm introduced in this paper. It is a variant of the bin search that Adams introduced in 2019. It uses hierarchical sampling as mentioned before. It has multiple passes, as this image shown before shows, with the feedback, and the information from the previous pass inform the current pass, and it maintains a queue of k candidates as shown in here. expressing a partially represented scale loop. As mentioned before, you go one loop at a time from the block to the thread to the serial loop from top to bottom. Yeah, to give some background, Halide represents the algorithm as a directed acyclic graph. Halide does not have cycles in their graphs. That's some property that is able to model well many image processing and computer vision pipelines. For example, this is the blur algorithm, which you have a horizontal blur and you have a vertical blur. And yeah, this looks weird because I actually will expect the negative one to be in the y, and rather than this might be a typo. No, yeah, maybe it might be a typo from the paper. You might have to be y in here to have the vertical blur, and this is horizontal blur. But anyway, the point is that you have this is your input, just first consumer and second consumer. Okay, so one thing about Halide is, as mentioned before, Halide separates scale from algorithm, and you don't see the for loops. It's like a functional language. And so in here, this is the induction variable for your first loop, and this the induction variable for the second for loop. So this is a matrix. If you have a color, you will have a third dimension. So yeah, so you have a nested for loops in here for this that are not shown because of what I mentioned. The schedule, yeah, you have to assign a tiling for that particular tensor operation. And what was mentioned before, the outer for loop is used for the block level, the intermediate is used for the thread. So the first loop determines where you go in the blocks. The second loop intermediate determines in which thread block are you, and finally the serial, which executes the course within the thread blocks. The author mentions two decisions to take regarding the schedule. One of them is where you compute the func, and then you go to the tiling. I don't remember he mentioned why that order was important. Why, let's say, you don't use tile first and then decide where to compute. Also, there are schedule decisions like loop interchange, reordering, like vectorization, parallelization, and what happened with the other scheduling decisions. Why he focuses on these two scheduling decisions and in this order, I don't know. But anyway, they are extending the Adams Autoscaler, which is quite effective, so they might be knowing what they're doing, I guess. And yeah, so start with decision number one, where to compute the stages. In this case, we have two stages, the intermediate and the output. So we're going to enter into a trade-off of parallelism, locality, and redundant computations, and we decide whether to fuse it, inline it, and we're going to talk about those details. First is the compute route. Compute route is a scheduling option of Halide in which the kernels are computed totally separate, and it offers poor memory locality and uses global memory, which is slow. It's basically launching the kernel separately, which incurs in a GPU overhead. And for the output, there's no option because it's the output of the program. The second option is compute at the outermost dimension that correspond to the block level. In this, you have the two computations in the same block. So once you are in the same block, you can use level 2 cache, another memory available, maybe shared memory, which is better than the global memory. And it introduces some redundant computation, not that much, and becomes the parallelism comes loops become straight at this level. Basically, yeah, because we are computing at the block level. Yeah. The other option is using compute at the inner dimension, which is a thread dimension, rather than the block dimension, which is the outermost. And in this case, instead of putting both computation in the block, we put them both in the thread level, and at that point you can reuse register and local memory, so it improves memory locality, but also you got more redundant computations and may introduce costly local memory speeding because there's no enough space. So those are things that have to be considered in the cost model, the hardware memory capacity. So the neural network can infer that, okay, if I compute at this particular level, but according to the sizes of the dimensions and the algorithms, you're not gonna fit in this particular hardware architecture, then I better use compute root or use compute at the block level. So that the neural network should be able to determine automatically if we provide this hardware target information. And the final option is inlining. This is the best memory locality because there's no memory, but it introduces unacceptable levels of redundant computation. And this is always the choice when you do a pointwise computation. They mention also that if funcs are stored at the block level of the producer, then they will be tiled immediately because it's convenient. Now we're going to talk about choosing serial loops, thread loops, and blocks loops, which are the three levels of allocation of computations in the GPU. For the serial loop, they are allocated in the registers, and as mentioned before, as seen before, and they can be unrolled so that you can use things like SIMD, I suppose. And if the serial loops are too large, then we're going to reduce the block and thread level parallelism, as mentioned before, and potentially increase the stride of memory accesses, which can reduce the equalizing of global memory and increase the shared memory bank conflicts. And they use, I guess, to reduce the state space, they use small powers of 2, 1, 2, 4, and 8, and odd if it fits. They mention some heuristics of how to select the thread loops. They mention that the innermost loop is the first dimension with extent higher than 16, and if there are none, they use the first dimension. And the first dimension in Halide is the fastest changing dimension. It's a little bit confusing in Halide because Halide is last major, that is the last dimension changes slower, but when you when it's displayed, it's like row major. You have the row changes slower and the column changes faster, so it's like a row major. But in here, if you understand this as this being the row and this being the column, then this is column major or a last major. So it's a little bit confusing there. So the one in the first dimension here is the fastest change, and that's what they meant when they assigned the first dimension to the thread, and the last dimension should be for the block. And yeah, these are the sizes that they use for the thread: 16, 32, and 64, and powers up to 16 for the other dimensions. Okay, then you select the block loop. Block loop, you should have the length of the number of blocks should be twice the number of SMs in the GPU, because for example you have 3 of them in here, you're gonna want to have at least 6 blocks. So because you want to keep them busy and balanced, and you also have to take the compute root and compute at decisions as mentioned before. In the previous slides, I talked about choosing the serial thread and block loops. I understand that they were perhaps assembling the schedules that are going to be considered in the search. That's my understanding. Now, going back to the hierarchical sampling, it's not feasible to apply get the features and evaluate the cost model for all the options. As mentioned before, there are going to be buckets and get representatives, and on those representatives you evaluate the cost model. And yeah, by the beam search you take the top k. That's how the beam search works, and then go for the first round. And as mentioned before, you go from the outermost, the block level. First consider that block level for the search, and in the next pass you get on the next level of the loop. until you reach the bottom, and candidates that are not promising are moved to the back of the priority queue. Like any good search, you want to have some pruning, and you want to enumerate the candidates that are both efficient and possible. So you're going to prune in these situations and listed here. States that have excessive recomputations, usually caused by inlining, that states that leave SMs idle, states that have pure utilization. These occupancy and utilization are measured in the features of the cost model. You're going to see it later. States that are too large to be enrolled, we want to enroll the serial loop. States that basically are dynamic or too large and cannot be promoted from local memory to registers, and states that exceed the GPU hardware limits, like having too many threads or too much shared memory. They also apply some optimizations, like if any serial loop has a total extent less than 60, it will be enrolled, and I think understands some sort of fusing as well. Okay, now we're gonna talk about the features that are used to feed the neural network to predict the runtime performance, and then we're gonna talk about the cost model, and finally we're gonna talk about the results. As mentioned before, the Autoscaler is done on top of Adam's 2019 Autoscaler, and it fits both the features of the schedule and the algorithm. The features of the algorithm, which include histograms of various arithmetic and memory operations over the entire algorithm, that's inherited from Adams. And the schedule is basically, I understand, either introduced or improved, at the very least improved, to include GPU specific information like how schedule uses different types of memory available on the GPU, that is a local, shared, a register, etc. How effectively is using the block and thread level parallelism, the level of occupancy it achieves in the GPU units, and also these computations are done for each Halide func, that is for each stage of the pipeline. First, we're going to talk about the memory features. One of them is a stride that gives a hint of a poor suboptimal stride is going to result in poor coalescing of global memory and conflicts at the shared memory level. The ratio of bytes of load and stores, this measures the efficiency of both at global and shared levels, and memory footprint for the thread and block levels in terms of global, shared, and register, and also give a hint to the cost model about cache behavior and register pressure. Next, we use features to measure the effectiveness of parallelism. For example, they basically measure the idleness of the threads relative to the number of threads at the block level and the available threads available in the hardware. And basically low occupancy can be the result of a bad stage fusion. Finally, they have occupancy features for var block and shared memory for each stage, and the complete list is in the appendix A of the paper. And for training the cost model, they use random pipelines constructed from common image processing and machine learning operations, building blocks, and this, I understand, this is inherited from the Adams 2019 Autoscaler. Now let's talk about the cost model. As mentioned before, this neural network that takes as inputs the features from both the schedule and the algorithm to predict the performance. It would have been nice if the paper showed a snapshot of the neural network used for this. At the very least, show exactly what are the inputs and outputs and the types of the network in the input-output. But well, at least they mentioned that they basically take the logarithm of the scale-specific features to compress the dynamic range, and they feed it into a fully connected network to produce the embedding vectors, and then after that they are stacked together into more fully connected networks to produce a vector of positive weights. And the coefficients along with features in a cost model predict the performance per stage and sum of stage. And yeah, it's the same cost model at Adams 2019, but with more GPU specific components. And yeah, maybe that's why it doesn't show. Maybe it might be shown in the Adams 2019 paper. And the feature and weights are then used for computing the following cost. Yeah, I saw that it was predicting the runtime directly, but it looks like the weights are used to compute the computational cost, which is the number of computations and the utilization of the warp lanes and SAMs, and also the loss store that measure that is I guess is the ratio of them that is measured for global sharing register, and the parallelism number of threads, kernel blocks launched and working set, the register pressure and cache usage. And yeah, basically this cost model is listed in Appendix B of the paper. Now let's go to the results of this autoscheduler. And for the results, the author is using 3 different configurations. One of them is the fastest one, which is one shot. You just keep the program, and using the cost model, you rank them, the sample schedules, and pick up the fastest one. And but the next alternative is this alternative is the fastest in compile time, but the least effective, and this is the most effective but the slowest one, and this one is in between both computation time and effectiveness. So in the second one is gonna do the same as the previous one, but it's gonna pick up the top 5 schedules, and then it's gonna benchmark for getting the real performance, and this itself is going to take more time to execute, and then pick up the fastest one. And the last one is the most time consuming, because it is basically it goes into a loop that involves benchmarking, but also involves training the cost model to improve it as we go, and this is going to get you the best but in slowest compilation time. Again, the 3 options are named one shot, top 5, and auto-tune. One of the things that the paper wants to achieve is reducing compile time, and another one is get faster schedules by improving the strategy to explore the state space of the schedules. Hierarchical sampling and freezing significantly reduces the number of states, and both of them are helping with the compilation time, and table 1 shows this during beam search. And on average, they evaluate 5% of the total states, and in the best case, less than 1% for bilateral grid example. Okay, I'm jumping ahead a little bit to the related work, because it's good to understand this to interpret better their results. The Adams autoscheduler of Halide that was extended in this work does not capture well the complexity of I would say the GPUs. They have the Lee 2018 autoscheduler that was developed for GPUs, but the results are 33% faster than this, and they're basically not ready to handle GPU. The cost model was not ready for it. It was not doing GPU based pruning of the state space. It didn't have the strategies presented in this paper, freezing, hierarchical sampling, memorization. And also Sioutas in 2020 outperformed the Adams 2018 autoscheduler. I'm curious if they try against me 2019, but I assume that since the authors are aware of this, that they are picking Sioutas at the baseline. So this is going to be the baseline. These are the results in terms of effectiveness, in terms of throughput of the schedule. So as mentioned before, this is relative to the state of the art. Sioutas. So Sioutas is gonna have a throughput of 1. Sioutas is the blue one. Yeah. Yeah, I guess they normalize the throughput somehow. Yeah, it's not that Sioutas has 1. You can see. And also it compares against Sioutas, a GPU autoscaler, but also against handcraft scales by human experts. And the human experts at times are considering scaling options that are not available to the autoscaler of this paper, and more details are going to be given later. So the 3 options of the autoscaler in the paper are one-shot, top 5, and auto-tune. And you can see that in the auto-tune is going to beat the handcrafted scale many times. The benchmark is a superset of previous work. It includes image processing, computer vision applications. You have the Harris corner detection, the lens blur, but you also have deep learning convolutional layers, depth-wise separate convolution. For this one, convolution, he mentioned later that parallelizing reductions, parallelizing R-DOMs in Halide are not considered, and I understand that the 2018 was capable of handling reductions. I don't know why this node is doing, but I guess that's a future improvement. He mentioned that's one of the reasons why the convolution did bad. Sioutas did not have the convolution option here. So relative to the Sioutas paper, the auto-tuning looks superior, way superior than the Sioutas option, but still, we're gonna see that the auto-tuning option takes a longer compilation time than Sioutas, so it's gonna have a better performance at the cost of higher compilation time. So the question is, the one that matches in terms of compilation times by reducing the scale, the state space explorations by reducing the state space, is the one shot is the one that can compare with compilation time regarding the Sioutas. So this one has to beat this one. But one shot beats it sometimes. Sometimes it beats it. Sometimes it doesn't. Yeah, you can see it here. So it's not like a decisive victory of this paper of the Sioutas paper. There's something that needs to be improved to basically get the best of the two. I understand that this one doesn't explore the whole state space. I guess the author was forced to do good state space exploration because of this one. That's my suspicion. In here we can see the throughput of the schedules with one shot and top 5. The one shot is the orange like one, and the other one is the purple one. The darker means that you're not using hierarchical sampling and not using freezing, and the lighter is that using both of them. Okay, so it is weird because in some occasions turning them both off is going to be better. For example, in the stencil chain, it's better not to use them at all. And I think other example could be that is in the one shot, both in the one shot and the top 5. Other example is I think there was another example. Yeah, the local Laplacian as well. It's better to turn them both off. There are other examples in which turning both on is the best option. Maybe on sharp mask is one of them. Lens blur, IR blur are examples of turning them both being good. And I think there are examples in which the convolution is an example in which it's good to turn them both on, and the same goes for separable convolution. Bilateral grid is a curious example in which it is better to have either freezing on or sampling on, but not both off and not both on. So I think it might be good maybe to have some heuristic on when to turn this on or off, and maybe have like a cost model as well to telling you when to use these strategies or not. But these numbers show that it is not always good to have them on. Using freezing and hierarchical sampling is not always good to get the best schedule, but these results show that it's always good to reduce the computation time. So in average, as mentioned, it's gonna be 5%. It's gonna evaluate 5% of the total available options, so it's gonna execute way faster. And in the best case for bilateral grid, which was the example that I showed, that either freezing was good or hierarchical sampling was good, but not both off or not both on. In that case, it evaluates the smallest fraction. Maybe there is something wrong in this example. Yeah. They increase, reduce the compile time by 49x. In the best case, 500x. I guess is relative to the previous autoscaler of Halide. But compared against Sioutas, a table 4, it did not do that well. It's more or less the same, and we're gonna see that in a moment. The throughput was slightly improved, even though that a smaller state space was considered. And the memorization helped, but it has a memory penalty, and we're gonna see that in table 2, but it's not really that much. So here we can see the effects of having the three state space search strategies: memorization, sampling, and freezing. If you have them both on, you're gonna get the best average. And there's some small deviations in here in which having sampling off has a lower computation time. But if you look at it, it's like a noise, 2.56 versus 2.12. So what I would say is that for this case on chart mask, the sampling, hierarchical sampling, offers no help. And for this case, this one is very close. It's like noise again. So in this case, it's like memorization doesn't have any effect. And bilateral grid was the one that was affected by sampling and freezing. So let's say if we turn sampling and freezing off, you're gonna get a huge. It will be, I guess, this one. It's gonna execute 10 times slower. Yeah. Yeah, and this is basically the speed up, which is basically showing the same. And this basically shows the result of the cost model, the effectiveness of prediction. What I guess the point that's trying to make is that the blue dots are the without node retraining, and with retraining you get closer to the prediction. You're good predicting if you are in the diagonal. The X will be the predicted versus the actual, and so you have to be close to the diagonal to be effective in the prediction. So this is basically showing that after retraining you are going to do much better. Here are some of the strategies that the user considered that were not available in the Autoscaler this paper. One of them is that they split and unroll the reduction loops, and they use atomic floating points to expose data parallelism. They use this warp shuffle instruction to share data between threads in a warp without requiring a full barrier across the entire thread block. And I think this is a big one. The simply and storage and packaging are not considered as well. This is huge. So yeah, still the autoscaler was able to be the human expert most of the time, and the human of course spent a lot of time, and if you have a huge pipeline then it might not be practical to do this. Here are the compilation results against Sioutas, and you can see that Sioutas did better in terms of compile time. Even against the one shot. The one shot was able to beat it a few times, and the top 5 a few times, but this one did not perform as well comparing to this one in terms of getting an efficient schedule. This one beat Sioutas most of the time or all the time, but it took more time to compile, so there was a price in there. Table number 5 shows the penalty of using memorization, and most of the cases the penalty is very small, as you can see, but there are some pathological cases for example, in BGU, you go from 3,000 to 18,000 on the view search. For related work, they mentioned polyhedral work, including tiramisu, which is CPU only, not GPU, and they mentioned that the compute and storage, which are Halide schedules, that are very important for efficiency of this kind of algorithms, image processing, computer vision, as we seen in the stencil examples. It is difficult to express in polyhedral compilers. Early automatic scalers in Halide use genetic algorithm over randomly generated scalars. Polyimage we combines the idea of polyhedral literature and Halide. They develop an autoscaling technique using heuristic cost model and greedy stage grouping algorithm, then compile some benchmarks over different tiles. This was extended for a better model, and they have the author, they point out to this publication from them from 2018, but there was another publication recently, and neither of them are pointing to each other. So it's like they're not aware of the latest work, so probably more work is coming their way to reconcile the difference. But also, if they are using polyhedral, then they're gonna have trouble anyway with computer, which is a very important part of this work. So they might not be able to get there. It's interesting to see what's gonna happen. Also, Muyapudi and Sioutas consider they have a heuristic cost model, greedy stage grouping to handle broad range of algorithms and schedules. And Sioutas uses the same search algorithm but extended to support GPU and expanded search space and a hand design a GPU cost model. So it's kind of a similar work, and that's why this is the baseline. In addition to this, the best performer for GPU that he found. And the search space for Sioutas is smaller compared to theirs, since it supports only a single level of tiling, and also there's the Lee Autoscaler in 2018, which considers trivial fusion that is optimized. I remember that this was basically targeted for training neural networks that was able to optimize schedules for reverse gradients to basically calculate the reverse gradient in a network. In that one, if my memory doesn't fail me, I think it was able to support RDOM in the schedules, which this paper doesn't support. They mention an interesting work on AutoTBM, which uses parameterized search over schedule templates, and they use reinforcement learning, statistical cost model, and gradient boost trees, and tree-based recurrent neural networks. And compared to other machine learning approaches, this work uses a more abstract loop representation, explicit program analysis, and GPU architecture knowledge. Here are some of the limitations of future work. The state space is not fully explored, of course. That's how you reduce compilation time. And also the decisions are per func, not including the update stages. And this update supporting updates is a blocker for being able to work with reduction variables, styling and rolling them, which is what helped the manual schedules to optimize the convolution layers and IRR blur. They need to extend the cost model to predict register speeding more accurately. And also the retraining was an issue, especially in the one-shot mode. Here's the link for the Sioutas paper, which was a baseline for the results. Here are some of the features that were mentioned in the paper. This is Appendix A. It includes information about the GPU, about the memory usage, the occupancy, the thread blocks, all the information that was mentioned. And here is the cost model, which is in Appendix B of the paper. And here's the total cost, which includes store, load, alloc, parallelism, and working set. And you can see how all of these are derived based on some other variables. And from what I saw in the paper, it seems that the inputs to this cost model come from the neural network, and this is what is used in the search to determine the best candidates. The conclusion and takeaways that I have from this paper is that it was able to extend data in 2019 to provide GPU support and make the schedule search smarter by using hierarchical sampling, freezing, and memorizing. And yeah, it was not able to beat the Sioutas in terms of compile time, and it was not able to beat the performance of the schedules of Sioutas without doing worse in compile time. But what they mention is that they are able to explore a larger state space by doing these strategies that Sioutas is not using, I understand. And there's also many limitations in the paper that are trivial. For example, RDOM support that if that is supported here, or SIMD or things like that, then this could maybe do much better than Sioutas. And yeah, they extended the cost model for GPU feature, and basically for some image processing computer vision pipelines, they're able to be most the state of the art and handcraft schedules. But yeah, I think there's still work to do, and hopefully all the work from this publication and also maybe even Sioutas work can be integrated in the main branch of Halide, so that becomes available for the autoscalers in the future. Thank you very much for watching.